So sorry, I was in a meeting. Now I got out. Okay. Give me a second. Let me set up my thing. Set up my thing really quickly. What lecture number is this? And the rule for question 3. What's the rule for question 3? Okay, during the break, I'll do it. Lecture 22. Okay, today we're gonna learn more graph theory. Okay. Turn the thing on. Preview. Share screen. Okay. Yep. Okay. So let me remind you, last time we learned about graph theory, right? That graph theory is a theory of doodles. So you can, so this is a graph, right? You have an object and the relation between objects. Okay, like this is a graph. Okay, and we learn, let's focus on the vocabulary, the lines that links between the two vertex. So the circle here are the vertex. Some people call it the nodes. Okay, and the link here is called the edges. You'll see why in maybe, I think, next class, why they call it the edges. It's stuck from one problem and people call it the edges for a very long time. Okay, and then the number of edges incident to a vertex is a degree. It's called degree. Okay, so for example, this thing, degree of this vertex is called V1. V1 is 2. Okay. Yeah. Today we're gonna do some fancy problem. Okay. So let's consider the following problem. Okay, the following problem. Let's think about finals because we are close to final, and our final is take home as usual. Let's see. So if you think about if you are OAA, right? Let's not think about it. If you're OAA, you have one really big problem when you try to schedule the final. So for example, there are gonna be people who take data structure, right, and discrete math. So for example, Justin take that, and there is someone like Keith take data structure and maybe not data structure, discrete math, and maybe some. What else do you take? Organic chem. You're probably too old to take organic chem. Probably take it like 2 years ago. What else do you take? ICCS 101. Okay, good. Programming 1. Let's call, what should I call it? Programming. Okay. And there are some people, let's say Airbus, take discrete math, data structure, and what's the class called? Let's call it EC1. Okay, so now imagine you have not 3 people, but you have like tons of students, right? You have like a couple thousand of students. You want to make a final schedule, but there's one problem. Let's imagine the following scenario. If OA said discrete math, 10 a.m. to 12. Okay, this is not actual time though. Let's say discrete math on Monday. Okay. And OA also put data structure on exactly the same time, 10 a.m. to 12 on Monday. What's going to happen though? What's going to happen? What's going to happen? A clash, right? A clash for Justin and Airbus, right? So we do not want them. So we do not want them to have. So if there's a student, right, that takes two classes like this, data structure and discrete math. So we do not want discrete math and data structure, right, to have the same time slot. Should not have the same time slot. Okay. Think about this. You have 1,000 students, so things like this gonna happen, right? So should not have the same time slot. So let's say if you just do not want any exam to have the same time slot, what would you do? What would you do? What would you do? The easiest one. You have about, I don't know how many MUIC open, maybe 200 subjects by other section. Right. So the simplest way to do it is each class gonna get its own time slot. Right. You could do the following. Each class gonna get the same the different time slots. So for example, there's a programming one. There is also an easy one. Okay. Let's consider if I only have 3 people. Okay. Then you imagine MUIC has 1,000, has like 200 of these, right? Then from the day you start the exam until the end of final week, how long does it gonna take? Like you can probably fit like 6 subjects in a day, right? It's gonna take you months to do it. Right? So that means final week is not gonna be final week anymore, but it's gonna be final months. But although no one's gonna complain about they having clash about the exam. Are we good? Right? Everyone understand that, right? The final week is going to be final month. That means you cannot go home if you leave abroad, right? You cannot go home after the exam. Because the exam take a month and a month is like the whole break you have. So this is a totally bad idea. So each one has its own time slot. Okay, this is like too long. Fix the problem though, but it's way too long. Okay. So anyone has a better idea though? We want something like in between, right? We want something in between. So for example, in this graph, okay, in this graph, right, you can actually avoid it with less number of sections, right? You can actually avoid it with less number of sections. So for example, if I move EC1 over here, then I'm safe, right? Now I save 1 time slot. You can go home like 2 hours earlier. Are we good? Right? So what we want to do, right? We want to make sure no one has problem with the exam time slot, and we kind of want the least number as well. How would we do it though? How would we do it? Anyone has a good idea? And this is about graph, right? So we want to draw something. So we want to draw some graph. What would you do? Anyone has a good idea though? What would you do? How do you solve this kind of problem? Map classes to time. Good. We want to assign, right? Our goal is assign time slot to class. Okay. So I think it's quite clear. I think it's quite clear that we want the node to be the class, right? The node should be the class. So let's do this. The node should be the class. So let's do 3, and then I'm going to show you some other graph. Let's do 3 people. Okay. The node should be the graph. So that is a data structure. and there's a discrete math, right? We use best solution, use hash map. What are you talking about? There's a data structure and there's a discrete math, and there is a programming. Oops. Programming, and there is EC1. Right? What else do we have? No, we don't have anything. So that's the feeling you get for the first algorithm class. That should be the feeling you get for the first algorithm class. Wait until you take the second one. That's not true. Okay, so what about this? We have to know how should I draw the edges though? I need to draw the link. How should I draw the edges? How should I draw the edges? Right? The edges means the relationship between two classes. Very good. If there is a student, so an edge, if there is a student taking both, right? Okay, so let's draw all this. So there is the guy who take that, right? Data, discrete math, and EC. There's a guy who take data structure and EC1, and there's a guy who take discrete math and programming. So let me skip it here. Okay, and that's it. Okay, so this is the graph. You may ask, okay, Adan, you just draw a doodle. What do we do with this? This is much better than you think. Think about this. By drawing doodles, right? You want to assign the time slot. Okay, and then you say, Adan, we ran out of the things to draw, right? You already draw the vertex. You already draw the edges. What else can you do? No. We can do color. Now we are being like 100% kids mode, right? Now we can put colors on it, right? The color here gonna represent the time slot. Okay. The color here gonna represent the time slot. And to answer Keith's question, if there is an edge, it means that at least one, not two. At least one. So what that means is the following. If you think about coloring, right? I can draw this. Okay. So let me ask you, what happened if I do this? What happened if I do this? Let me get the list of people. 2 seconds. Let me get the list of people. Okay, copy. I just want to copy this. Copy. If I do this, right, then there is the guy who takes discrete math and EC1, which is Airbus, gonna complain, right? So that means, think about this. This now turned into a game that you want to color all the nodes, right? So you want to color all the vertex. All vertex. What are the constraints in coloring though? What are the constraints? Very good. If there's an edge, there is an edge, the color cannot be the same. So far so good. If there's an edge, the color cannot be the same. Okay, so that means I can do this, right? I can do something like this. Okay, we're gonna look at like a bigger graph, and then we're gonna play together. By bigger, it's like not that much bigger. So we can do purple here, and I can do a red here. Okay, so that means for this kind of coloring, right, the color that I give it, then you're gonna need 4 time slot, right? You're gonna need the 4 color, the blue, and the purple. Okay, can we make it less? We can make it time for 3 times slot, right? So for example, the only problem is probably this guy can reuse it, right? This guy can reuse, I don't know, either blue or green, doesn't matter. Either blue or purple. Okay, now we get rid of 1. Can we do even less? If not, can you tell me why you cannot do less? Good, because you have this triangle, right? That triangle kind of tell you that you need 3 color. Okay, this triangle over here kind of tell you that you need 3 color. Okay, so let's do this. Let's do a bigger graph. So this kind of problem is called graph coloring. Okay, this is one of the problem that makes so much money, because think about this. Every economic problem, right, is about assigning resources, right? It's about assigning resources, and a lot of times you cannot do, if you assign resource to one person, you don't want to assign the resource to another person and so on. That's why it really uses no. Imagine me and Ajahn cannot try to explain to OAA. Imagine me and Ajahn cannot do OAA. But no, this thing has a little bit of problem. The thing is, think about this, they are tightly packed, right? You kind of want them to be far apart, which you can do that if you learn more numbers. Okay, if you try to do this, you're gonna run into the problem that finding the minimum number of class, finding minimum number of class. Okay, this is called it has a name. Wait 2 seconds. Chromatic number. It has a name. If you want to sound smart, but it just means minimum number of class, it means chromatic number. Okay, this is an NP problem. You cannot solve it in polynomial time, and you cannot even check the answer in polynomial time. Okay, you cannot even check the answer, right? So for example, imagine a graph of 100 nodes, 100 vertex. I say that, okay, you can do it within 50. How do you check it? You cannot do it in 49. Right? Then you're gonna need to run the thing. Okay, so this is an NP problem. Okay, so far so good. But for small problem, how long will it take to run through this? I don't know. I think for MUIC, not that bad. It's just 100 or 200 nodes. Probably not that bad. At most probably a day. I don't know. If you write in a decent programming language, not Python. Python, it takes very little time to write, but it takes so long to run. Okay, so let's do some graph. Let's try to see. Can you find a chromatic number of this? Let me draw some graph. Let me draw this, and then you're gonna tell me how many color do I need. Oops. Not that one. This one. This one. This one. Okay, now your job, figure out what's the minimum number I need. Right? So we want to color them such that no 2 edges share exactly the same thing. Six. You are rich kid. What do you do? Can you tell me? What do you put here? 5. Okay, doesn't say 5. Just run through all of them. How many vertex are there? 1, 2, 3, 4, 5, 6, 7. Okay, So that's a claim. Okay, 6, 5, and 3. Okay, now let's do the least one. Let's do the least one. Let's tell. Now what? Tell me, what would you do? Let me label the vertex. What color did you give A? Blue. Okay, good. Blue. B? Orange. And what color did you give C? Yellow. D? For D, it's clear, right? You can reuse A, right? You can reuse whatever A you use to save the color, right? And E can be, which one do you want E to be? I think yellow, right? Yellow, right? And the other two, now you don't need to make a new color anymore, right? Because you just need to make sure that it's not yellow. So it's going to be blue and orange, right? So you just save everyone 3 classes, right? From Keith answer, you just save everyone 3 classes. So that means, and you may think, Ajahn, this is like a toy problem, right? You may think, Ajahn, this is a toy problem. Why would someone want to solve something like this? You're just coloring, you're just playing kids' toy. Believe it or not. Let me ask you another question. Let me ask you another question. You may like this one better. Okay. So let me tell you something about cell phone tower. You can do this as well. If you don't have the color pen, you can just label it with a number, right? So 2, 3, and 1, and 3, and 1, and 2. You can just label it with numbers. Okay, so let's do this. You may think, okay, this is just a mathematical toy, Ajahn. You just draw doodles and color things like kids, like 5-year-old kids. Okay, trust me, it's used. So let me give you the one that this problem gonna turn into like millions of dollars. Okay, so here's the problem: the cell phone tower, right? If you place a cell phone tower, let's do this: a cell phone tower. This is where you place it, and this is the radius. Let's think about it as a Wi-Fi. You probably kind of know this if I say that this is a Wi-Fi. Okay. Okay. Let me put it like this. Let me put it like this. Okay, let me draw something like this. Okay. And then let me even put this guy here over here. Okay. You know, this is actually one of the best. Think about this. Wi-Fi works like this. Wi-Fi, you know, when you set up the Wi-Fi, right, it asks you about the channel 1, 2, 3, 4, 5, 6, up to 11. If you're using 2.4 gigahertz, right? When you set up the Wi-Fi, it asks you about the channel. You can actually like command click to your Wi-Fi and it's gonna tell you channel. Unless you're using fancy Wi-Fi like I'm using right now, then you're gonna see, you can option click on your Wi-Fi icon and then you're gonna see the channel. Okay. So the thing here is there is 1, 2, 3, 4, 5, 6, 11, but the only one that are usable are 1, 6, and 11. You don't want to choose something in between because you screw up everybody. Because here's how it works. Each one has a spectrum. This is number 1. Number 2 looks like this. Number 3 looks like this. And number 6 looks like this. Number 11 looks like this. So that means you probably want to choose a channel that they do not interfere with each other. The x-axis is the frequency. Okay. In real life, if you have more than 2 houses around you, then you're screwed. Go and get 5 gigahertz Wi-Fi, much better. Okay. So that means you only have 3 channels, and this is why you probably heard about the cell phone company like AIS or True and DTAC go and auction on the Wi-Fi frequencies. Okay, right? And each Wi-Fi frequency, I think it cost them about 7 billion baht each for each channel. Let's call it that way. That's okay. 7 baht each channel. Okay. So that means here's the thing. The guy over here. If this one, suppose they use channel 1 and this guy also use channel 1, right? Then he cannot actually receive the signal because you don't know which one, and these two are going to interfere with each other if the two are using exactly the same channel. Is that clear? This guy over here will not be able to use internet, will not be able to use the phone if the two are interfering with each other. So this guy gonna be like sad people if they use the same frequency. You may think, Ajahn, that's easy. You just buy however many frequency there are from Gosotosho, whatever it's called in English, from the guy who actually sell you the frequency range. Changing the channel will give you some interruption though. So you can say, okay, Ajahn, this is easy. I just buy this many channel. I just buy 9 channel. Then you figure out, oh wait, 9 times 7 billion, that's a 53 billion baht. That's sad, right? No. You don't want to do that. Can you figure out what's the minimum number of channel you want to buy? Right? Think about this. If you figure out the minimum number of channel you need to buy, then you're going to save like a whole bunch of baht, right? You're gonna save a whole bunch of money. How do we solve this? Maybe drawing that graph again. So what would be the vertex? What would be the vertex? Each area is going to be the cell tower, right? Going to be the cell tower. So these are going to be our node, right? These people are going to be our vertex. Now, how do we draw the edges though? Okay, we draw the edges if they touch each other, right? If they have some overlap. So that means if I make this guy and that guy the same frequency, there are going to be some sad people inside, right? There are going to be some sad people. So let's draw that. Let's do that. Okay. Let's do that. Okay. I kind of need a color, but whatever. Okay, let's do this. And let me just do this for you. This guy and that guy. And this guy. Here. And this guy. Here. And this guy. Go to here and there. Okay, now tell me, how many channels do you need? Three? Okay, Saran. Okay, let me put the name. Let me put the name. A, B, C, D, F, H, I. Okay, so I'm gonna believe Saran. Saran, tell me first, what is the channel for A? Red, okay. And B? Green. And C is blue. And D is, you have no choice, right? You need to be blue. What is E? What's E? E is red. And F is also red. F is green. and G is blue, and I is going to be green, right? It has no choice, and this string can be anything like blue. Good. So you just go from 9 to 3, and the saving is 6 times 7 billion, 42 billion. Right? That's good. So the thing that I'm telling you, it's gonna come up, and you don't know when it's gonna come up. You don't really know whether it's gonna come up, but when you see it, the thing that I want you to get from this class, the thing that I want you to get from this class is the fact that you can turn some problem into a graph problem by drawing doodles, and then you can solve it much easier, right? Think about this. If you get the problem in a table like this, then you have no idea how to do it. But if you draw doodles, then the problem becomes like much easier to do. Okay, if you draw doodles like this, the problem become much easier. Even the traffic light use this. Okay, you know traffic light will need to do this. Okay, any questions so far though? Any questions so far? There's an art museum theorem, which I'm going to skip. Any questions so far though? Any questions so far? If not, we're going to take 10 minutes break. And I'm going to answer what number 3 Keith wants to know is. Okay, everyone good? So let's take 10 minutes break, and you're going to come back at 14:50. Oh, by the way, Sudoku can do this as well. Sudoku, the game that you play, is actually graph coloring theorem, actually graph coloring problem. Monopoly. Oh, if you get double, right? I think I tell you what you need to know, right? If you toss the coin, if you toss the dice and you get a double, like 4-4, then you get to toss it again, right? So the next turn you can toss 5 and 3. Then the total is gonna be you're gonna walk 16. Are we good? Right? But if you toss 4-4, 5-5, and then 6-3, right? You're gonna walk in total, I don't know, 8, 10, and 9, 27, which is like almost around the board. I think half the board, right? 27 because each side is 10. Okay. But if you get really lucky, like 4-4, 5-5, and 1-1, then the thing that happens is that you go to jail. You cheat for sure. That means you walk 0. Okay, so that's the rule. Monopoly, I think I asked you what is the expected like step that you can walk, right? Right. I think that's what I asked you. Right. I just asked you about the advance. Okay, and skip problem 5 or skip problem 5. Problem 7 gonna take you a while and it's due on Sunday as usual. Yes, I did. Yes. Did I pause the solution? Let me see. Did I pause solution for number 7? No, I haven't. Okay, let me pause it. Publish. 7. Publish. Okay, so I published number 7 already. All the solutions are on Canvas. It's mine. That's not right. to run at my company because my company hire a lot of CS graduates. They put Ajahn Kanat picture on the wall. They actually do that. There's a flag with his face. I don't know. Ajahn Kanat never go to the office. Okay. So let's do this. Let me tell you a story of a mathematician, okay, who visit, what's the town called? The town is called Königsberg or something. I'm pretty sure I pronounce it wrong. I'm pretty sure this is the town. Okay. Before it was bombed. Right. Before it was bombed. Right. So the town looks like this. This is island A and island B. Well, let's match the lecture note. Island D, island B. Okay. And I suppose you just can't walk connect here. And then there are bridges along them. So there is this bridge, this bridge, this bridge. Okay, way back then people need to use the bridge. This bridge, this bridge, that bridge, and that bridge. Okay. I don't know. Did you learn it somewhere in Ajahn Kanat's class or some class? Ajahn Kanat's book. Yes, because this is a very famous problem. This is actually the birth of graph theory. And this dude is the guy who first draw the doodles that actually solve something. Okay, so let's imagine the following problem. Okay, some of you have seen it, some of you have not seen it. So let me tell you the story. The story is the following. This guy wants to visit the bridge. Okay, want to walk on the bridge, but he is lazy as well. He wants to figure out a way to walk on each bridge, exactly once each. Okay, that's all. Walk on the bridge. Exactly once each. Right, for maximum experience with no repeated experience, right? If you play a game, you want to like visit every episode once, right? Think about this. This is a tree for like the game, the visual novel game, right? You want to make sure that the tree kind of not overlap. Think about Stargate. This is the movie of the week. Think about Stargate. You don't want to revisit exactly the same timeline twice. That's the movie of the week. Go watch it if you have not. Okay, so let's try. Let's try. So you can say, okay, let's say if I start at A, let me name the bridge as well. 1, 2, 3, 4, 5, 6, 7. Okay, so let's say you start at A, so you're gonna walk along. Let me use this. I'll walk along bridge number 1, go to number 2, then to number 4, number 5, number 6, number 7, and then you realize, okay, I forgot bridge number 3. Okay, then let's try that again. I think if you try it enough time, then you kind of give up, right? Okay, let's do this. Okay, now I complete this, and then I'm screwed, right? If you go number 3, then you miss number 2, right? If you go number 2, you miss number 3, then you sort of screw. You can try this. I don't know. Whoop, whoop, whoop. You can try this, and then you screw. You forgot number 3 again. Okay, so after a while, this mathematician, by the way, his name is Euler. You know Euler, right? That letter E, like E to the 10, that letter E, there are many things named after him. There are two Euler formulas. We ran out of name. There are even two Euler formulas. The guy is named Euler. You know he's smart, right? So he said, okay, if I cannot do this, maybe there's a good reason why I cannot do it. So far so good. So he want to figure out what exactly causes him not to be able to walk on every single bridge. Exactly once each. Okay. 400 years later, this is a breakthrough in medicine though. There's a breakthrough in medicine related to this, which I'm going to tell you a story later. Okay, so anyone know why? What exactly is it that prevents you from doing it? Anyone knows? Okay, so first let's draw this as a graph, okay? Because we want to draw a doodle. Determination. It might have something to do with determinant though, I don't know. There's a determinant of something called adjacency matrix. The determinant actually tells you something, but I'm not sure if it has to do with this problem. There is a lot of magic going on with graph theory. Every time I see it, I learn something new every time. Okay, it looks like this. This is something called not a simple graph though. This is called multi-edge. So you have two edges, but that's okay. That's okay, right? Okay, so he draw this as a graph and then he said, there must be a reason why I cannot do it. Okay. So let's consider this. Let me tell you. Otherwise, it's going to take you quite some time to figure this out. But I'm pretty sure you guys are going to figure it out eventually if I give you like a week or so to figure out why is it that you cannot walk over all the bridges. We don't have a week to do it. Okay, so let's imagine if you start at D. Okay, let's see. If you start at D. Okay. If you start at D, and then you walk all of on every single bridge. Walk on every bridge. Once each. What needs to happen though? What needs to happen? If you start at D and you walk on every single bridge once each, what's going to happen? Where would you end up? Can you tell me? You have to end up at D. Why is it now up? Why is it now up? You will need to end up at D, but why? Because it has to do with the odd number, right? So the first time if you start at D, right? The first thing that you need to do, you need to go out from D, otherwise you cannot go anywhere. Right? The first thing that you do, then you can do all the things that you want, then you need to come back to D. Right? The second time you need to come back to D. Are we good? And then the third, once we are at D, then we need to go out, otherwise we do not use all the bridge, right? So that means, okay? So that means if you start at D, you will not end up at D. This is the thing. You cannot end up at D. So far so good, right? If you start at D, you cannot end up at D. Okay, so far so good. And everyone can see that this has to do with the degree, odd degree, right? If start at odd degree, X, let's call it X, cannot end at X. We travel through each edge once, not each point. Each edge. Okay. So that's good. Now, if we do not start at D, okay. Now let's look at this. If we do not start at D, if we don't start at D at odd degree, vertex X. Okay, so let's say if you do not start at D, right? Here's what you need to do. You need to go into D, go out from D, and get into D again. So that's good. So that means if you have an odd degree, if you do not start there, then you need to end there. Sound good so far though? Is everyone good so far? Okay, everyone good so far? Now tell me, why can't I do this? Why can I walk all over the bridges? Okay, now you learn two very important facts, right? If you start at odd, you cannot end up at odd. But if you don't start at that vertex, you should end there, right? So given an so that means given an odd vertex, it needs to be either the starting point or the end point. Every node has an odd degree. Very good, right? So you can only pick like one start and one stop, right? Right, one end, right? You can only pick one start and one end. And now you have like how many candidates are there? 1, 2, 3, 4. Therefore, you cannot walk. Okay, so far so good. But this also gives you a very important insight, right? This gives you a very important insight. Okay, let's do something like this. I don't know. I think you see this on Facebook, right? You see things like this on Facebook, and then people ask, okay, please draw every edge without lifting your pen and repeating the edges. Okay, believe it or not, it's exactly the same problem. It is exactly the same problem. This kind of walk over each bridge exactly once each. This is called Euler walk. Okay, so that means, okay, given this kind of walk, then you know that if you don't start at odd vertex, you need to add an odd vertex. So anyone know how to do this? How to play this kind of game? Right? So let's think about all the vertices, right? All the vertices, you have this guy, this guy, this guy, and that guy, and that guy. So this is A, B, C, D, and E, right? Where should you start and where should you end though? Why should you start and where should you end? Why should you start and where should you end? You probably see this somewhere, somehow before, right? Please draw this without lifting your without lifting the pen. How should we start though? How should we start? Given the two facts that you just learned. Given the two facts that you just learned. How should you do it? So for example, if you start at B, right, you can do this, 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 and then you're screwed. Right? Good. So you learn that if you play this game, you either start or end at the vertex, at the odd vertex, right? Okay, so that means you need to start at D and end at E. If you try to start somewhere else, you can try. It's not gonna work. Okay, so we can do this, 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 and that over there. So far so good. That's good. How about any questions so far? Or any questions so far? So we know that we need to start and end at the odd vertex, right? How about if I add one more edges? Add one more edge. If I add this edge, can you do it? Can you draw this without lifting your pen? No. Why is it Saran? Why is it? Why we cannot do it? Even node with odd degree. That's actually a true statement, and it has to be that way, right? Now what? By handshaking lemma, we need that. We learned it like 2 class ago, or maybe last class, right? By handshaking lemma, you cannot have odd number of odd degree vertex. What particularly about this graph that makes you not able to draw it in one swoop? So where are the odd degree vertex though? Where are the odd degree vertex? Where are the odd degree vertex? They're actually 4 carat. You cannot have 3. Right? There are 4 odd degree vertex. Okay. And you learn it's like this guy, right? You know that if you start at D, you must end at E, but okay, it's A and C is not end at starting point, and that means it's wrong. So we learned that if we have more than 2 odd degree vertex, then no. Okay. This is actually one of Euler theorem though. If there are more than 2 odd degree vertex, then it's a no. Okay, you cannot do it. You can try all you like, but you know the trick here is that if you start at an odd degree, you need to end there. You cannot leave it in between. Okay. What about this? What about if every node is even? What's going to happen? Okay. Let's imagine this. If every node is even. Okay. 1, 2, 3, 4, 5, 6, 7. That's 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. I think that works, right? 1, 2, 3, 4. 1, 2, 3, 4. Can you do it? Okay, so let's consider an even degree node. Okay. If you start in an even degree node, what's going to happen? Let's say you have 4 links coming out from you. If you start here, what's going to happen though? If you start at an even degree node, right? The first thing that you need to do is you need to walk out, right? And then you need to get in, you need to walk out, and then you need to get in. So that means if start at even, must end at that even. Everyone with me so far though? Everyone with me so far? If you start at a node with even degree, then you must end at an even degree node. Okay. And also the contrary is also true. If you don't start at there, then you don't end there. by the same argument, right? By the same argument, right? If you don't start that, you need to get in, get out, get in, and get out. So you're gonna end up with getting out. Okay, so you're not gonna end there. So for this one, you can actually prove, and the proof is not that hard, but it's in the lecture note, that if it's all even, then the Euler walk exists, and it's also a cycle, so you can actually do this. It's actually a cycle, right? So remember, we start there, we end there. Okay, so let me conclude. Okay, what we have seen so far is that the actual proof, the more rigorous proof, is in the lecture note. The Euler walk exists if and only if there are 0 or 2 odd degree nodes. Okay, and I think this is called Euler theorem. Yeah, so far so good. So far so good. And again, you may ask, okay, Adan, this is like mathematician play toy, right? This is what discovered 400 years ago. Okay, and then right now, I think this thing is less than 100 years, probably 50 years. Okay, so let's think about DNA sequencing. Okay, let's think about DNA sequencing. Let me show you the cost of DNA sequencing over time. This is the time. This is the cost. Okay, so way back then, it's just impossible. This thing is like impossible. Okay, until someone found a method called PCR, the cost dropped like crazy. The cost dropped. This thing is PCR. The cost dropped, but still, then people improve on PCR a little bit, and then something happens, make it like so cheap. This is like today. Okay, why DNA sequencing is important? Because think about this: a lot of disease happens at DNA level, right? If you know the DNA, you kind of understand everything about your body. Okay, and it's quite important. I think in the future, it's going to be very important that you're going to need to be able to do DNA sequencing quick and cheap. Okay, there is also a documentary about DNA sequencing on, I think it's Veritasium, that to catch a culprit on a case, you don't really need the DNA of that person. You just need the DNA of all the relatives. Okay, and that's the thing that makes it possible, right? So this thing, say the entire human genome sequencing, this thing costs probably like $4 billion or something, not 4 baht, 4 times 10 to the 9. And nowadays they sell you for like $30. Something going on here, and this has to do everything to do with Euler walk. Okay, let me tell you the story. Okay, here's the thing. Sequencing DNA, right? When you do PCR, I don't know if you know what PCR. PCR, they try essentially what they try to do. They try to replicate your DNA. Okay, and replicating DNA is like the thing that we learn, the mean time to failure thing. So whether it's going to take the next gene, there's some probability. Whether it's going to take the next gene, there's some probability that it's going to fail, right? So this thing may be like 99%. I make up the number then, right? And then 99%, and then you keep replicating your DNA, okay, until it doesn't replicate anymore. There's some probabilities, right? So even it's 99% on average, you're gonna only have the length of 100. Okay, so you're gonna sequence like probably 100. What's that called? 100 acid bases. What do they call? They're gonna sequence only some of this thing. I don't know what's it called. Nucleic acid. But the length is going to be limited. Okay, the length is going to be very, very limited. That is why it's almost impossible to do PCR on entire human genome, because you have like 4 billion genes. 4 billion of these guys, which is not going to happen. Okay, so they figure out, okay, I say this is hard. How about we sequence something, we do something along this line. How about we do something along this line? Because, you know, getting the long one is hard, getting the short one is easy. So that means when you put your DNA in a tube, okay, then you're gonna get a very short segment. So sometimes you're gonna get the head, sometimes you're gonna get the next section, sometimes you're gonna get the next section, sometimes you're gonna get the next section, right? So for example, if your DNA is this thing, this is another movie, by the way. Good movie. Go watch it, Gattaca. Go watch it. Watch this. This is another movie. Go watch it. It's really old. It's like year 2000 or something, or maybe even older than that, but it's a really good movie. Okay, so let's say your DNA is this short and you have, I don't know, 1, 2, 3, 4, 5, 6, 7. Maybe when she was young. Okay, then you put in here, you're gonna get some answer, right? You're gonna get some answer. So for example, you're gonna get GAT, you're gonna get ATT, right? That GAT is from there. Okay, ATT is from these three, right? You're gonna get a whole bunch of segments. TTA, TAC, and ACA. Okay. So that means actually let me show you the screen. The screen, if I show you full screen, you cannot see it. Okay, so what that means is that this thing is a DNA chip. It's called DNA chip. Depending on the length, but for now we do length 3. The DNA chip works like this, right? So you look at all the combination of this letter, right? You have 4 nucleic acid, okay, GTAC, and there are, how many ways are there? How many ways are there to pick 3 from here? You can pick repeated one as well, right? So there are 3 slots, and each one of them has 4 choices, right? Each one of them has 4 choices, and that means you're gonna get 4 to the third. This is only for length 3 though. If you do length 4 and length 5, it's become much huge, much larger. Okay, you get 4 to the 4 cube, so that means is what, 256, right? What's that? 64? What is it? 64. You're gonna get a plate of 64 by 64. Okay, and each column is going to correspond to each combination. Like GGG is here, right? ATT, maybe GGA is here, or so on, right? You're gonna get an array of 64, right? And then you're gonna see which one lights up, right? So for example, the one that say GAT is going to light up. Okay, and this is the result that you get from doing the DNA test. You actually get a million because it's much longer. The real thing is much longer than this. Okay, so far so good. So you only know the fragment. You don't know the order. So far so good. So that means, let's pretend you don't know this. When you do DNA test, you only have this. Okay, you only have tiny fragments. Okay, and there has to be a way to connect them, right? There has to be a way to connect them. So far so good, right? And we want to use the fragment and reconstruct the original one. So far so good. We want to use the fragment that we get and reconstruct the original one. Okay, What do you do though? What would you do? How would you do it though? Given that you don't know the original sequence, how would you do it? How would you do it? Okay. Pick a random one and see if they overlap. Imagine that you're going to have like tons of days, right? If your DNA is really long, you're going to have tons of days. Some of them are going to light up, some of them are not going to light up. Then you could pick some random one, like you can pick start with ATT and then see what you get, right? So here is what this professor does. His name is Pavel. I don't know, he deserves some Nobel Prize or maybe the Nobel Prize for computer science. I don't know what's called. He deserved this. The thing that he did is very simple. So for example, you have GAT, ATT, TTA, TAC, ACA, and CAT, and ATA. Suppose you have this. You want to know what the original one is. Here's what he does. Okay. So you would think that, okay, Ajahn, it's clear that these guys are going to be vertex. No. That's not what he does. He does the following. He said, okay, because I know that this thing are going to connect it with like k minus one string, right? So for example, if this thing is of length k, then the thing that actually tells you that these two are connected to each other, right? The thing that tells you that these things are connected to each other is the two letters. So he starts with drawing the two letters, all the two letters, right? There's GA, there's 16 of them, right? GA, and then there's AT, and then, I don't know, there's TA, AC, and then CA, and then AT, again, we draw it already, and then TA. Okay, so far so good. And then what he does is he starts drawing the edges. Okay, the edge look like this. So for example, GAT, oh, I know. If GAT exists, makes these two nodes exist. GAT. Right? It's a GA and AT that gives you GAT. Right? This guy goes here. Okay. And the next thing is, okay, he knows ATT. So it's going to do this. ATT. Oops, sorry. There's a double T somewhere, right? There's a double T. Sorry about that. There's a double T. There's a double T. So this guy becomes ATT. Right? And then TTA goes like this. And then you have TAC, and then you have ACA. Okay, and then you have CAT, which is this guy. And then you have ATA. Okay. Imagine this is the data you get, right? I just transform this into this graph. And then I ask you, what is the original sequence? What would you do though? Ask you, what is the original sequence? Then you're going to start doing the following. Okay. There's a modification of this algorithm, but this is the idea. Okay. Then you're going to start the following, that you want to walk from somewhere, right? You want to visit each one exactly once each, right? Right? Exactly once each to decode what exactly is the original sequence. So for this case, it's pretty simple, right? It's going to be GAT, right? GAAT, and then GA, and then CA, right? You now CA. And then what? CA, and then I add up the T, and then TA. So far so good, right? You can do this for a lot longer, and then you can modify the sequence that sometimes you walk along the bridge twice as well, and then you minimize the number of like the the maximum of the minimum number. You get what I meant? Okay, so far so good. So this is essentially Euler walk, but a little bit modified because it's a directed graph, and then you can actually walk along each bridge like 2 times. Let's say if you allow something to walk along it 2 times, what's going to happen, and so on. Okay, this is essentially Euler walk. Okay. This thing is going to become very important when you get so, and medicine is going to reach there. Especially because if you look at medicine, right, it starts from like you put some external thing to fix your body. But if you can modify your body to fix your body, that's even better, right? Which I think when you guys get old, the technology is going to reach there. Okay. Any questions so far though? Any questions so far? And I actually heard a story that he actually has a daughter and his daughter has some genetic disease and he wants to like cure his daughter. I'm not sure if the story is true or not, but I don't know, whatever he did, this thing is cool. This thing is like really cool. Okay, so far so good. So, any questions so far though? Any question? I want to keep the next one for next time. Are we going to reach a point where we raise a headless chicken? We are almost there, actually. We are almost there. We are almost there. If you know, there are people who grow the meat in the lab. There are people who grow meat in the lab. And the fake one is actually not that bad, right? The one that is, what's that called? The plant-based meat. Those are not that bad. When is your final exam? Your final exam is going to be during the final week. So it is going to be due on the 19th or 14th, right? The Sunday. It's going to be due on Sunday, which is 12th. Due on December 12th, right? The thing gonna get posted like at the very beginning of the week, and then you're gonna have like a week to do it, almost a week to do it. Pick your time. Okay. So any questions so far though? Because I want to keep the next one. The next one gonna take a while to actually appreciate it. Okay. So next time we're gonna do some more application of graph theory, which is going to be mind blown. Some of the plant-based meats are pretty good. Okay, any question? Any questions? If not, we're gonna call it a day, and we're gonna see you on next Tuesday. Okay, and that's gonna be the last thing on the exam. Okay. So see you.